Hello. Hi, everyone. Um, Welcome to this session. Thank you for coming. My name is John, and I'm going to go over Global Secondary Index, GSI. And I'm pretty sure that you guys have heard a lot about GSI. This is probably not the first sessions that you heard about it. So I'm going to go over it in a little bit more details, kind of like, open the hook and have you to pick inside how we do it. So, but before I start, this is a standard disclaimer. So we have a 4.0 beta just came out today. And we're still doing improvement and fine-tuning on the product. So it's basically just a standard disclaimer saying that our final production product may have some deviations from what I present over here. And this is today's agenda. First of all, I'm going to go over some introduction materials, some basics, some rationale why we do GSI. Then I'm going to cover a little bit on partition index. And you may hear some of the earlier sessions saying, well, we talk about partial index. Essentially, it's the same thing, partial index and partition index. And then I'm going to talk a little bit more into like how we build an index, how we keep the index up to date with the document updates, and how we're going to do index scan, how we're going to support availability, and what happens when there's data rebalancing, right, at the data surface, and what happens when there's a failover, in one of the data service nodes. So as you can see here, is that it's a fairly full agenda, and there's a lot of materials to go through. So if you don't mind, please hold your questions until the end of the presentations, and I'm more than happy to answer the questions at the end. And you may have seen this many, many times today. So this is our Couchbase Server 4.0 architectures. And as you can see here is that I have a cluster of homogeneous nodes. And in each node, there are three types of surface. There's a data surface, which is your container for Couchbase bucket. And we have index surface, which is a container for secondary index. And we also have query surface, which is a container for the Nickel execution engine. And when you deploy Couchbase Server, you have a choice to say, hey, what service you want to activate on a particular node. So in these particular examples, I have this cluster with 6 nodes, and I have three data surface, and I have 1 query surface, and 2 index surface. So let me get started by asking, well, why we want to build global secondary index. So one of the major rationale why we do it is to enable you to do fast query lookup and fast query scan with high throughput. And the way that we support is by being able to do range partitioning on the index. So if you look at these particular examples, I have 2 Nickel statements. And what it does is basically just to look up a customer document based on last name. And here is that, and at the bottom, what you see is that I have 3 index surfaces. And with these 3 index surfaces, I actually have the last name index created in those surfaces. And when the application issue the Nickel statements, right, the query surface will process, will parse, and will plan, and then will execute the query statement. And as part of the executions, there's an index metadata that is actually kept inside the query surface. And what the index metadata does is that it knows about all the distribution of the index. It knows about all the index definition within that cluster. So with that information, the query service is able to pinpoint exactly where your data is going to reside in which node, and it can send the scan request just to that node, right? And in this case, right, it allows us to be able to serve your scan requests very fast. If you have a lot of, if you have a big cluster, there's no scatter getter because we know exactly through the index metadata where the data resides. Another reason is workload isolations. In this diagram, you see I have 3 data servers and 2 index servers. And your data service do what it's doing, today, right? Is take the memcache get setups that will, get those mutations will get applied to your data service, and the data service itself is hash partitioned. So this is your regular transaction workload. But on your right-hand side, what we have is we have a query workload. We have a query services. The query services do an index scan, and index services provide the results to the query services. And in between what we have is that we have DCP. A DCP is a replication protocol in Couchbase. So any get and set operations that you apply to the data services will get replicated through DCP to the index service. And the mutation itself will be range partitioned in the data service, right? Again, right, this is for your fast scan lookup. And the data will be organized in such a way that provide you the fast response time to query services. The key things here is you have very different workload, and you can partition your data very differently. And the way you partition the data really is trying to get the best performance out of the types of workloads that you have, right? For query, you really want to have fast response time. For transaction workload, you want to have a very fast or very high write throughput. And the things that ties them together is really through to DCP. And another reason for using GSI is that it enables independent scaling. So you can add capacities to your cluster as you add more index to it. And you can basically add capacity by adding additional nodes to your cluster, or you can basically add more powerful nodes, right, just for the index. So you have both the scale, you have a scale up and the scale out options. GSI will also allow read availability. So in this example, what you see here is that I have, on the right-hand side, I have 2 nickel statements. So I create 2 index on the customer bucket, and it's index on the email field. So internally, the query services and the indexer itself will treat these 2 index as equivalent. And if you deploy these 2 index on different index nodes, as you can see in the bottoms, I have 2 index services on both left and right, and one has email 1, the other one has email 2. So 2 things that could happen. One is if one of the index services go down for whatever reason, the other ones can become a backup, right? It can become a replica. So if you have a scan traffic for email 1, it can route to the node that has email 2. And the other one is doing load balancing. So if you have scan requests, they can load balance between these 2 indexer nodes. And another reason, why we want to use GSI, or why we have GSI, is that we want to leverage our ForestDB, which is our next generation storage for Couchbase. And the next sessions following up on this one is going to talk about ForestDB. So if you are interested, please stay, and there's a really deep and great discussions on ForestDB after this. So let's now talk a little bit about some basic. So we all know that for GSI, we can index on JSON documents, and we can basically index on any fields or any JSON fields. It can be a string, Boolean, numeric, null, array, and subdocument. And once you index the field, this is the sorting order for the values. You start with null, and then false and true and number and string and array and subdocument. So let's now goes to take a look at the index DDL. This is a very simple create index statement. It's basically create an email index on the customer bucket using GSI. This statement itself does two things. One is it will create index metadata on one of the available index node. And the other thing it will do is that it will kick off doing an index build. And this statement will return only after the index build is completed. But there are times that you may want to say, hey, I just want to create a bunch of indexes, and I want to save the index build at a later time. So there's a way to do it, and you can use the defer build options to do it. So in this case, it's almost look the same as the previous create index statement, except that now you see there's an option called defer build equal to true. And this one, what it does is that it will only create the index metadata in the available, in one of the available index nodes, but it will not build it. But to kick off the index build, you have to issue a second statement. So you have to say build index on customer, which is customer is the bucket name, with index, email, and phone. So you can actually build multiple index together. And the reason why you want to do this is that it's more efficient to do it when you build those index together. And I'll go a little bit into more details why it's more efficient later on. There are other flavors of create index. I think you see some of it in some of the NICO presentations. I'm just have two examples here. One is that you can create a composite index. Here is that is a composite index on two fields, state and zip. Earlier, you also see that Kishore, when they go through a NICO sessions, he also has create index on the functional, on creating a functional index. Another thing is that it's very common, after you're done with the index, you can drop the index. So now let me talk a little bit about partition index, or somebody call it a partial index. So in this diagram, what you see is that I have a single bucket, which is the blue diagram. And in this bucket, I have three different groups of documents, right? They basically separate into three different levels. So what a partition index or what a partial index is essentially an index on a subset of JSON documents. Here is, as you see, I have three groups of documents, and you can create one or more indexes on that, on that subset. And the way to do it is look at the NICO statement on your right-hand side, right? The way to do it is that you specify a where clause when you create an index. And this where clause essentially is a NICO expression. And what this NICO expression does is that it selects the documents that is applicable to the index, so that when you build the index, only a certain documents will be applied. And there are many ways that you can partition an index. So this is one example. You partition an index based on document types. And there are many, many ways to do it. And I'm just showing you just one example. So in this case, I have a single bucket, which is called default bucket. And this bucket itself has three different types of document. It has order, customer, and shipment. And at the same time, each document has an attribute called type. So you see there's order, customer, shipment. And what I want to do is that I want to build an index for email, but I just want to build it on the customer document. So the NICO statement on the right-hand side, on the blue box, basically does that. So you can say create index email on default, which is a bucket name, email, which is the field name, where type equal to type equal to customer. This is very similar to how you want to index, in a relational database, because in relational database, you want to actually build an index on the table. Here is that I want to build an index on particular types of documents within your bucket. So they are functionally equivalent. Another way you can partition an index is partitioning by range. In this example, what I want to do is I want to index email again. But what I want to do is I want to partition it based on range. For example, if the email start with A and R, I want to put it, I want to deploy in one node. If it start with J and R, then I want to put it, onto another index node, and S to C at another node, right? So I can basically use 3 different create index statements to create 3 different partitions based on range. And there are other variants of the use case as well. For example, I may want to say the where clause. Maybe what I want to say is that I know that I have a lot of customers in California. So I want to say, hey, I want to actually build an index just for California. So in this case, I would say create index email where stay equal to California. And what bites you in doing that? Because what you could do is that if you know that, there's certain, within your data set, if you know that there is a particular range of data that is actually has a high usage, right? You can actually build more index replica just based on this range. So in this case, I can say, hey, let me build 3 equivalent index, right, just on California. And there may be other states, for example, let's say that Alaska, which is much less populated, I may want to group it with other, I may just want to have just one index for it. So basically, it allows you to have multiple ways to build your indexes for availability, for load balancing, and for other purposes. And other benefits, the reasons why you want to partition an index is that you get a faster index build time. With smaller index, you can build the index much faster. You can lower your maintenance latency. You can get faster scan. You get faster, higher scan throughput, right? I mean, it allows you to basically manage your index working set much more carefully. So by default, when you do a create index, the indexer will automatically pick an index service for you, and it will put that, it will create the metadata, and it will build the index using that index service. And the way the indexer does it is that it look at the distribution of the index across all these index surfaces and pick the node that is least populated. So in this case, I have 2 create index statements. I have create index on order ID, and also have create index on shipment ID, right? When I first issue the first create index statement on order ID, it will go and pick a node. So it pick one of the nodes, 198.33.25.17, and create an index in that node. And when I create a second index, which is a shipment ID, then you see that actually there's another index surfaces exists, and there's no index to it, so you'll put it into the second node. So you will put order ID in one node, and we'll put shipment ID in the other node. But sometimes what you want to do is that you may want to have explicit control where you want to place your index within the cluster. Each node in Couchbase, right, can be identified by an IP address, and this will be the same thing for a query surface node and also an index surface node. So in this case, if you actually want to build an index on a specific node, you can specify that IP address in a create index statement with a with clause. So I'll show you the syntax, on the right-hand side. So you can say create index customer ID where type equal to order with the actual IP address of the node. And what it does is that it will pin the index on that particular node for you. Now I cover create index. Now let's take a look how we build the index. What I have here is that I have a single data surface, and I have 2 index surfaces, node 1 and node 2. And in my data surface, I have 1 bucket, which is the blue rectangle. And in this bucket, I have 3 different types of documents: order, customer, and shipment. And what I want to do now is I want to build 3 different index on customer. I want to build an index on last name. I want to build an index on phone and email. So on your right-hand side, you see there's 3 create index statement, create index last name on last name where type equal to customer. But you also notice that I'm using a defer build options. That means that when I issue this statement, I only create the metadata, but I'm not actually building the index yet. But at the bottom, what you see is that after you create this free index, and at the bottom you see that I have a build index statement. So it says build index on the default bucket with last name, phone, and email. And what this build index statement does is to say, hey, let's go and kick off the index build for on these 3 different index simultaneously, right? Make it concurrent and parallel. And when you build an index, the first thing it does is that it's open up a DCP stream between the data surface and the index surface, and there will be one dedicated DCP stream between the data surface and the index surface. The DCP, as we just talked about before, is a Couchbase replication protocol. And if you have, and all the indexes within that index node will be sharing this same DCP stream. So in node 1, I have 2 index, which is last name and phone. And these 2 index will be built sharing the same DCP stream. But if you do have 2 different index surfaces, each index surfaces will have a concurrent DCP stream running together, just like this diagram. Node 1 will have one, and node 2 will have another DCP stream. So this allows both index surfaces to build the index concurrently. Now let's open the hook a little bit more and take a look a little bit more what inside the data surface. So what you see here is that there's a broker sitting inside data surface called projectors. And what the projector does is that it's actually listening to the DCP stream from the data surface itself. And any mutations that is coming from this DCP stream, the projectors will take a look at it, and then it will look at the index definition and figure it out which are the fields in this document are being indexed. And what it does is that it will extract only those keys out of the document. And then it will route the keys to the corresponding index surface. So in this example, you see that I have a customer document with last name, phone, and email. There's on the left-hand side. When this document is inserted into the data surfaces, this document will be replicated through DCP to the projectors. The projectors will take a peek and see that, oh, actually, node 1 has 2 index, last name and phone. So what it does is that it will create a document fragment with only last name and phone, and will forward that document fragment to node 1. And similarly, it sees that node 2 has index for email, so it will basically just create another document fragment and forward that over to node 2. So you can see what the projector does is actually, a little bit like MapReduce. It's basically, take a document, extract the information, extract only the information that is relevant, and forward, that information to the right indexer nodes. And the whole purpose for it is really to reduce the network traffic, right? Because now we don't have to send a full document from a data surface to the index surface. And also for the keys, right, I don't have to route all the keys to every data surface. I only route the relevant keys to that specific index surface. So it really tries to reduce the network traffic between the data surface and the index surface. Once the document fragment arrive at the indexer, the first thing the indexer does. So here, what I'm going is inside, right? I peek inside the index surface itself. Once the documents arrive at the index surfaces, the first thing it does is that it put it into a mutation queue. And there will be a set of background workers called extraction workers that will actually take the document fragment from the mutation queue, and then it will extract the keys out of this fragment and put it into individual index queue. And there will be another set of workers called persistent workers that will take these keys and then put it into a storage layer, which is ForestDB. This whole structure is highly parallel. It can be parallelized based on the based on the buckets and the V buckets and the number of index. It's highly concurrent under the cover. And also notice that, if the key is got, when the persistent workers got the key, we'll also first check that whether the key actually has changed in the index, right? If there's no change, then it will be a no op. We will not apply the key. So if the key is changed, then it will forward it we'll basically apply it, or update the index on disk. So by doing this check, it's also minimize the necessary I/O to the storage layer. Now, once we build the index, we have to keep the index up to date. So if there's ongoing mutations coming in, right, we need to keep the index up to date with these ongoing mutations. And the way it's being done with index maintenance is really similar to index build. Again, there is a dedicated TCP stream between the data surface and the index surface just for index maintenance. And again, the projectors is also playing a role for reading from this TCP stream, extract the document fragments, and then forward those changes to the index surfaces. But one thing you also notice that, let's say that if you have many active index right inside the indexer nodes, all these active index will be all updated using the same TCP stream. So this document fragment will contain all the keys that are necessary to update all these indexes within an index surface. At the same time, from this diagram, you also see that we can have concurrent TCP stream for both index build and index maintenance. So what it means is that, while there's an index build going on, the existing index will also keep up to date and vice versa. So we can actually keep things going on in parallel. And obviously, one of the things is that, let's say that if the index is finished build, right? So the maintenance, the maintenance TCP traffic will get updated. So now, the other TCP, the maintenance TCP stream will update a new index that is just being built. While the index is actually being updated, the indexer will create two types of snapshots. One type of snapshot is called persistent snapshot, and what the persistent snapshot does is for recovery. It creates versions of the index on disk, so that if the indexer needs to roll back to earlier versions of the index for rollback, it can actually take a look at the persistent snapshot and then pick one. The other one is called in-memory snapshot. The in-memory snapshot is really for scanning. It mainly is used by query stability and consistency. Or if you guys are familiar with Oracle, essentially it's statement level consistency and cursor stability. And the way it works is very similar. Conceptual-wise, very similar. I mean, Oracle is actually using a timestamp, and here we're also using a timestamp to keep track of those in-memory snapshots. So let's pick a little bit further down into the indexer. So inside each indexer is also has metadata managers. What the data manager does is that it receives all the DDL requests. So if you create an index, or if you drop an index, or you build an index, all these requests goes to the metadata managers. And upon receiving those DDL requests, the metadata managers update the metadata repository. And once the metadata repository is updated, the metadata managers actually will push the updated metadata to all the query surfaces. So if let's say that if you have 2 query surfaces and 3 indexer nodes, one of the indexer nodes got metadata changes, and that metadata managers will go and update both the metadata sitting in both query surfaces. And inside the query surfaces, in this diagram, what you see is that there's also something called index client. And inside the index client, there's a metadata cache. The metadata cache is to keep track of all the index definitions across all the indexer nodes. Now let's take a look at index scan. So in this diagram, I have 2 query surfaces. And query surfaces has the index client as well as the metadata cache. And I have a single index surfaces which has 2 indexes. It has phone and email. And each index has 2 snapshots, T1 and T2. And I have a statement on the right-hand side. And what it does is that basically it tries to look for a customer based on an email. So the first thing the query service does is, okay, let's go and figure out whether there's an index defined, right, for email. And if it does, it will go and ask the index client to say, hey, let's go and do a scan. And the first thing the index client does is that it goes to metadata cache and say, hey, well, where does the data reside? I have a cluster, right? I have a cluster of indexed nodes. Which node actually has my data? So it will use the metadata to pinpoint the exact node that has the data and will send a scan request to that indexer node. And the scan request is made up of, it contains the high value of the scan, the low value of the scan, and a consistency option. And on the indexer side, right, it receives the request from the client. And the first thing is that it looks at the consistency options, and from the consistency option, it picks a snapshot. And there are two types of consistency option. One is called unbound, right? With unbound, what the indexer will do is that it picks the native snapshot that is in the indexer at the moment. And if the consistency option is request plus, then the indexer will observe any current or future snapshot that matches with the request. So once the snapshot is being picked, what the indexer will then do is that it will create an iterator on the snapshot, and it will start streaming the result back to the index client. The index client, on the other hand, will create a response channels to the query services and then put the result in the response channel. Think about the response channel essentially is a buffer, and the query service can start reading from this buffer. As mentioned earlier in the presentations, if you create two indexes with identical definitions, in this case I have email 1 and email 2, they are both an index on the email field. The indexer and the index client will treat these two indexes as equivalent. And again, what it means is that you can use these two indexes as a read replica for each other. So in this case, I have email 1 deployed on one index node and email 2 on another index node. If one of them goes down, the other one becomes a backup. Or if you have index scan coming in, it can load balance the scan traffic between these two index nodes. So now let's go and peek a little inside what happens to the indexer when there's rebalancing happening at the data surface. So here what I have is that I have two nodes, node 1 and node 2. These are data surface nodes. And it has a single bucket. Node 1 has a V bucket 0 to 511, and node 2 has V bucket 512 to 1023. And I have a single index surface. And you can see that each data surface has its own projectors, and they stream the keys to the indexer node. So node 1 streaming the keys relevant to V bucket 0 to 551, and node 2 streaming keys for V bucket 512 to 1023. And now let's say that we want to take out node 2. So as the rebalance going on between node 1 and node 2, right? So since we take out the node 2, so what rebalancing does is that it will make, it will basically propagate the data, existing mutations to node 1. But while that is going on, index surfaces will continue to receive keys from both projectors. But once the rebalancing is done, the projector, it will send a stream end to the index surface saying that, hey, there's no more keys coming from V bucket 512 to 1023. And what the index surface does at this time is say, okay, now I need to go and figure it out. Who is the new master for V buckets 512 to 1023? So it goes to the cluster managers. The cluster managers now tells, okay, next service to say, hey, node 1 now is the master for all the V buckets. So what the index surface does is say, okay, now I know node 1 is the master, and I know that node 1 has a projector, so let me talk to the projectors. So I know that the projectors are already streaming keys, right, for 0s to 511. So we'll ask the projector now go and actually also stream the keys for 512 to 1023. So this is how we do data rebalancing. But one thing you do notice that is that how the index is being maintained is totally independent of the data operations, right? So the index surfaces, will keep updating, and once it knows that, the source of the data has moved from one node to the other, and it will automatically adjust and figure out where the new source of data is. New source means where the new master is, and automatically adjust to say, you go and ask for this new master for the data. Data failover work in similar way, not exactly like data rebalancing will work in similar way. So in this case, what I have is that let's say that node 2s go down. And also let's say that node 1 is a replica, right, for node 2. So in this case, the index surface, instead of actually getting a stream end message, it will actually get a connection error. And when the index service get a connection error for node 2, it knows that node 2 has, okay, rebucket 5, 12 to 10, 23. So it will go to the cluster manager and, again, go and ask, well, what is the new master for these rebuckets? And the cluster manager tells the indexer, say, hey, node 1 is the new master. So the index service now will go and talk to the projectors on node 1 and say, hey, send me a failover log. And what the failover log essentially, it has the last valid timestamp that can be used for rollback purposes. And the index service will get that rollback timestamp from the failover log. And it will go and pick a persistent snapshot that actually matches that rollback timestamp. So here what I have is that, the index services have 3 snapshots, T1, T2, and T3, and assuming that T3 is the latest snapshot, but it says that, hey, my rollback snapshot actually only matches T2. So it basically will, pick T2 and roll back the index based on diversions. And after rollback, what it does is that it will go and now it knows that node 1 is the new master, so it will ask node 1 to say, let me go and stream the keys from for rebuckets 5, 12 to 10, 23. And it'll be using the timestamp or sequence number from that rollback snapshot and go and ask, well, let me go and start streaming based on this rollback point or checkpoint. If there's a network partitions between the data surface and the index surface, it works similar to data failover. It will get a connection error between the data surface and the index surface. But in this case, there's no rollback because, node 2 is essentially still the rebucket master. But what happened is, in this case, the index service find out, okay, there's no change in the rebucket master, so it will try to reconnect to node 2. And upon reconnection, if the reconnection is successful, or if the network partition is being repaired, then the index service will ask the projectors to restream any keys, right, from the points where the network partition happens. So this is the end of the presentations. Again, there's a beta, and there's the link that you can download the beta to play with. So it's open for Q&A. Any questions?
So from the projector, right? So we're listening on the DCP event. The document fragment. Let's say if there is a document update, right?
Yeah.
But it's not touching the field that's used in a particular index. Do you still forward those document fragments to the index, or it's intelligent enough to say that even though the document has updated, but that portion has not been updated, therefore I would drop that document fragment?
In this case, it will still be so the question is that if the document field has updated but it's not being indexed, right? Do we still forward the document fragments to the indexer? So the answer is we still forward it, but it will get filtered out in the index. We will not actually update the index. So at least there's no I/O traffic. Yes, go ahead.
If the index is too big to hold in one mode, what happens?
Typically, in this case, what you want to do is you partition the index. So it will partition it in a smaller chunk.
So we have to do it manually? Like
For 4.0, yeah, you do have to do it manually.
So consider a scenario where index is being created, and while it is going on, it could be deferred or it could be under create index. That node crashes.
The what?
The node,
The index node crashes. Okay.
So at that point in time, when it comes back up, will it be able to resume?
Yeah, it will resume from where it started. From not from where it started, from where it stopped. So you remember we built the persistent snapshot? Those snapshots will also be used while you are building an index. Yeah, so it will roll back to where it is and then restream from that point on.
At that point in time, my command has already aborted.
The command?
The command that I ran from CBQ,
Yeah.
that would have already aborted, right?
That will actually execute. It's continue executing. So it will be, the recovery will be happening in the background. So the command is aborted. So it will return to you. But the execution will happen in the background after the recovery.
After the node recovery.
Yeah.
Gentleman's question, actually. He was asking whether index goes down. And my question would be, what if the data service node goes down? Then your ECP stream, I don't know whether it's in memory, whether if the node crashes,
Yeah.
then once it comes back, whether the stuff in the memory being persistent to any permanent non-volatile storage or not when the node is restored, right? If whatever information in the TCP is lost, then this index replication stream will miss that kind of latest whatever update of the data.
Now, so you say that what happened if the, when the index is being built, right? What happened if the data service goes down? So in this case, the data service, either it's got failover or it got bring up again, right? And at that time, you'll get a connection error because the connection between the data service and the index service will be disconnect. And I just cover, like in the presentations, right, there will be the data failover. So the data service will first, after we connection, first go and ask for a failover log to figure out whether it needs to roll back the index. If it does, it basically roll back the index to a particular known point between the data surface and the index surface and ask it to restream from that point on.
So the failover log is now something new to 4.0 or 3.0?
It's a 3.0. It's a DCP functionality.
question about strings indexing. Is there any way to index a string field so I can do query like contains substring?
That I think you have to go and ask the Nickel team,
Nickel
because
guys.
that is in the
I was thinking it's
Nickel area.
the way we build indexes, or you guys build indexes. So, like for example, right?
Yeah.
Should probably be working, right?
So right now it's actually handled in the CPQ in the Nickel layer.
Okay, I'll check that out.
Yeah.
Thank you.
Yes.
Let's say we have two nodes with same index, and one of them goes down. And when it comes back, by the time it comes back up, the other index is updated, it goes back up.
I'm sorry. Can you speak a little bit louder? Sorry.
Okay, so we had two nodes with the same index
Uh-huh.
built there, and after that index is built, one of the nodes go down.
Okay.
And since there are two nodes, there's already load balancing, right?
Yeah.
Yeah, one of them goes down, and there is some updates to the data, and the other node that is up is already being built, already has it. When you bring the second one back up, does it automatically rebuild the index, or do we
It will go through the same rollback protocol. So it will figure out where the last snapshot is relevant and roll back to the snapshot and then restream from the snapshot. So it won't lose any data. But that index obviously will be a little bit behind than the one that is up, right? Because the one that is up is actually has been taking new mutation from the data surface. So the other index, the other inside while it's actually doing recovery will take a little bit more time to basically be able to catch up with the latest data. But it will basically roll back and then get updated.
will not happen until that is
the rollback will happen while you bring, when you restart the indexer nodes.
No, she's talking about the load balancing. Will that wait?
Oh yeah, it depends on your options, but yeah, it will wait until that happens. Yeah.
Do you get any notification that your indexes are falling behind if your data update rate is too high?
I'm sorry.
Do you get any notification that if your data update rate is too high
Yeah.
and indexers are falling behind?
Yeah.
What kind of notification you get in that situation?
What kind of?
Notification. How do you learn that the index is not up to the state of the data?
We're going to put down some statistic so we can check how far behind it is. So there's a statistic, for example, how many items needs to be built, so you can know how much behind.
Each index is actually replicated as well in other index nodes.
You have to build equivalent index, so you have to build 2 index. Yeah, if you want to basically use for load balancing and replica. So you build equivalent index, then they can be used as a replica. But they give you the option, right? Because you partition an index, you know how your data set is. There may be a certain data set that is more important for you, so you can create more indexes of the same definition, and then you get better load balancing and availability. Sorry, time's up. Thank you very much.